Okay, trig folks, this video is going to be on polars, so it's going to be our first introduction to polar coordinates, which are a little bit of a math red pill. They are a completely different way of plotting points on a plane. So the first place to start is where we normally are in math, which is in the Cartesian plane. Maybe you've heard that term in geometry, but we kind of come to assume that this is standard, that when we plot some graph here, we've got these x and y axes, and things happen at regularly spaced intervals, that it's 1 and 2 and 3, and we've come to accept this grid system as kind of how we do math. Now, polar coordinates are a bit different. They aren't representing things in this grid system, but rather with two different notations. So normally we have our, I'm going to stick with my rainbow pen here. Normally we've got our x comma y, but in polar, as you can see down here, we've got r comma theta. Now I'll go over what each of those means, but first let's look at this Cartesian point here. So we went, I suppose this is a point -1, comma 1. So -1 in the x direction, up 1 in the y direction. That's nothing new to us. So what we're going to end up doing is expressing this in terms of an r, a radius, and a theta, and an angle. Now how are we going to do that? So we've got this point here, and what we end up doing is drawing this line here, and then we can drop down a side here, and then we've got this nice triangle. So we now have a triangle with an angle, theta, and then we have our radius, which is going to be our hypotenuse of our triangle. So we have, in Cartesian, we have an x side and a y side, and then we have this radius. So let's do a quick conversion, and maybe that will clear things up. So I've got a Cartesian point, so when I say Cartesian, I mean x comma y, to a polar point in the form above. So what we're shooting for is r comma theta. So what's going to be helpful for us is remembering our Pythagorean theorem. So we know that if we've got a triangle here, we've got a squared, a, b, and c, we know that a squared plus b squared equals c squared. And I just told you that this r is our hypotenuse of a triangle, and we've already got these two sides. We've got our x and y side, which are √3/2 and 1/2 respectively. So all we have to do is plug these in our Pythagorean theorem, and we can figure out at least one part of our polar, and then we can move on to our next. So one step at a time. So √3/2 squared is just going to be, what is that, 3/4, and then 1/2 squared is 1/4, so we've got 3/4 plus 1/4 is equal to c squared, so c is just 1. And the beauty of making your own notes is that that is actually our point on the unit circle. Normally, the reason it's called a unit circle is just because we have this radius here of 1, and I had my x value of √3/2 and my y value of 1/2. So that ended up solving for our c, or our radius, of 1. Now how do we find our theta? Well, we've got this x value and a y value, and we know a nice trigonometric function which is going to help us solve that, which is tangent, because our tangent is going to be our x over our y, or our opposite over our adjacent, however you want to put that. So I'm going to jump over here for a second and say that tangent of something is equal to our opposite side, our 1/2, over √3/2. So that's going to be tangent of something is equal to, you gotta flip these around, so you're gonna have 1 over root 3, because your 2's will cancel, so 1 over root 3, or root 3 over 3 when you rationalize the denominator. So where is our tangent equal to root 3 over 3? The answer to that should be pi over 6, and we know that by unit circle. And another way to express this is arctan of root 3 over 3, which is the same thing as these two. This is just a layman's version of that, so that's pi over 6. So that's our angle, pi over 6. So now we have our 2 points, our r and our pi over, or our r and our theta, which are, our r is 1, and our angle is pi over 6, which should make sense to us. I'm just going to highlight this because all my work's gotten a bit messy, but that's our answer, that's our conversion to polar coordinates. But if we take a look at our points, we've got root 3 over 2 for x and 1/2 for our y point, and we ended up with 1 comma pi over 6. And our 1 is going to be our radius of our unit circle, and pi over 6 is the angle, which matches up. Pi over 6 will match up with our sine equaling 1/2 and our cosine equaling root 3 over 2. So kind of nice concept connection there, to use a Mr. Singer term. So let's go in reverse. We've got this polar point here, -2, comma 5 pi over 4. So how do we end up converting this? Well, we've got a few options. We know that we've got this, if we just kind of graph this out, we've got this radius, or hypotenuse, of -2, and we've rotated 5 pi over 4 radians here. So with a little bit of trickery, we can get there. So let's say sine of my angle, 5 pi over 4, and sine is our opposite over our hypotenuse, and we don't know our opposite, so that's going to be here our y value, so I'm going to say y over our hypotenuse, which we know is -2. So we can solve for this by saying y is equal to -2 times sine of 5 pi over 4. Now, our sine of 5 pi over 4, we should know by our unit circle, is -√2 over 2. So -√2 over 2 times -2 is just going to be root 2. And we can do the same thing with cosine, and we will find that our x value is also root 2. So there we go. We've got our x and our y from our radius and our theta. So our polar coordinates would be root 2, or excuse me, our Cartesian coordinates would be root 2 comma root 2. So how are we going to go about this? Or how are we going to go about checking this, rather? We've got our Pythagorean theorem. So I'm going to plug in my x and my y, so root 2 squared plus root 2 squared should equal my original radius, -2 squared, which is correct. Root 2 squared is 2. Another root 2 squared is 2. That's 4. And -2 squared is 4. Does 4 equal 4? Check. We did it right. So this is our answer for our conversion. The last thing I want to cover here is kind of how this graph is going to look. So at the beginning, I referenced this grid system. We've got these series of tick marks evenly spaced out. That's our Cartesian. In polar, we end up with a kind of wholly different system, not a grid. So each of these radial lines here represent an angle. You can see this one is pi over 3, this one is 2 pi over 3, and each of these circles represents a different length of our radius, or another way to put that would be a different length of the hypotenuse of our triangle. So maybe this one is 1. So everything going around this circle could be a hypotenuse or radius of 1. So let's kind of last act here. Let's try to plot this, and this is a polar point with r comma theta. So we have our r is 2, but theta is pi over 4. So we just need to find our kind of circle, which represents 2, which is right here. This whole circle. Not very accurate, but that's what we're looking for. And then we just need to find our radial line of pi over 4, which sits somewhere between pi over 3 and pi over 6. So our point will be smack right there. That's exactly how we would plot this. Now we'll get into graphing these and using our r and theta as variables and solving for those. But in general, all we are going to cover in this video is what polars are, which is simply another way to represent points with our r and theta, and how to get back and forth from Cartesian to polar. So there should be some Edpuzzle questions sprinkled throughout. I'm sure you've completed a few and maybe one after this, but we will talk about this in class following.